Question number 8 from section 4.2. Graph the equation y equals 4 to the negative x power. You can graph, this is an exponential function, so it's either going to be a growth or decay function. With a negative exponent, it ends up being a decay function. We can make a table of values with just a few x values. If you plug in -1, you get 4 to the -1. So that's 4 to the first power, which is 4. Plug in 0. 4 to the -0 power is 4 to the 0 power, which is 1. And plug in +1, you get 4 to the -1 power, which is the same thing as 1/4. These 3 points you can use, -1, 4, 0, 1, and 1, 1/4 as points on the graph of the exponential function. -1 up 4, 0 up 1, and 1 up 1/4. This graph starts high and decays exponentially and will eventually flatten out. As x goes to positive infinity, the y is going to get closer and closer to 0. It looks like this choice here, and we can choose the best answer. You can also use a graphing calculator to check your work. If you go to the y equals, and you enter 4 to the negative x power, do a standard zoom 6, and you have a nice exponential decay function. Okay, let's look at number 9. Here we want to sketch the graph of f of x, which is equal to 6 to the x, and then a +3. Be careful here when you're working through this one, because this 6 to the x is a growth function, but this +3 means the whole graph has been shifted up 3. You can make a table of values. For example, -1, 0, and 1. You get 6 to the -1 power plus 3. 6 to the -1 power is 1/6 plus 3. It's 3 1/6. That works out to be, as a decimal, 6 to the -1 plus 3 is about 3.1666, or 3.2 when you graph it. When you plug in 0, get 6 to the 0 plus 3. 6 to the 0 is 1, and 1 plus 3 is 4. And when you plug in 1, you get 6 to the first power plus 3. 6 plus 3 is equal to 9. So use those points. -1, 3.2, that's a rounding. 0, 4, and 1, 9. -1 up 1, 2, 3.2. 0 up 4, 1 up 9. Okay, now the graph is an exponential growth. It will end up flattening out as you get closer to y equals 3. In fact, right here, you can think of this as a horizontal asymptote. It's going to get closer and closer to this y equals 3. That +3 takes an exponential function that normally flattens out on the x-axis and moves the whole thing up 3 units. Compare your graph with the choices, and this looks most like it, and check your answer. All right, let's look at number 10. All right, again, be careful when you're working through these, because you want to pay special attention to where the exponents are. Here we have an x plus 4. The exponent, we've added 4 to the exponent. That's different than adding 4 to the whole exponential function. You can make a table of values, but when you think back about the effects of translating graphs, think of this like as an x plus 4 in parentheses. When we did this with graphing parabolas, the plus 4 in the parentheses actually shifts the whole graph to the left 4. So instead of doing my typical -1, 0, 1, think about shifting this whole graph to the left 4. So I'm going to use -4, -5, and -3 as a few points to get. Now, if you are just starting off with making a table values, you may not get enough points to get a decent looking graph. So just expand your graph, expand your table, and get more points. So if you plug in -5, you get 2 to the -5 plus 4. Do the exponent first. That's 2 to the -1, which is 1/2. Plug in -4, 2 to the -4 plus 4. Do the whole exponent first to get 2 to the 0, which is 1. And then finally 2 to the -3 plus 4. Evaluate the exponent first to get 2 to the first power, which is equal to 2. So these are your 3 points that you're going to use uh, when you're sketching the graph. -5, comma 1/2, -4, comma 1, and -3, comma 2. You can plot those. -5, 1/2, -4, 1, -3, 2. If you start off with the -1, 0, 1, you're going to get these numbers that are so far up the page that you really don't see where the graph bends and where it flattens out. So that +4 would indicate that the whole graph of an exponential function has been shifted to the left 4. Compare your graphs, choose the best one, and check your answer. Okay, now let's look at number 11. Now number 11, we're asked to solve an exponential equation. Solving exponential equations is different than how we solve those quadratic equations and linear equations. The key to solving exponential equations is to write both sides using the same base and equate the exponents. So this is my hint for solving exponential equations, especially for this section. The key to solving exponential equations is to write both sides using the same base and equate the exponent. So if you notice for this one, the left side is the base is 25 and the right side the base is 5. So if I could write both sides using the common base, then I can what we call equate the exponents. I'm going to write 25 as this is 25 to the x power, which is equal to 5. And I'm going to write 25 as 5 to the second power, roll that to the x power equals 5. Now, using the properties of exponents, I can rewrite this. Remember, if you have a to the m to the nth power, you have a power to a power. The property of exponents, you're going to multiply those powers together to get a to the m times n. And that's what we have here. We have 5 raised to the power of 2 raised to the power of x. That can be written as 5 to the 2x power. So the left side, the base is 5 and the exponent is 2x. The right side, the base is 5 and the exponent is 1. If both sides have the same base, you can equate the exponent. It's kind of like dropping out the bases, and you write an equation that this exponent is equal to this exponent because this base is equal to this base. We have the equation, it's like dropping the bases, that 2x equals 1, okay? And then solve this for x, we get x equals 1/2. So the hint here, write both sides using the same base. If this base is equal to this base is equal to this base, then this exponent has to equal this exponent. So it's kind of like you drop the base, drop the bases, and you end up with an equation where the left exponent is equal to the right exponent, and you solve that for x. And we check our answer. Now, the next few problems are going to be done the same way. The key to doing these is look for those common bases and use properties of exponents to simplify and equate the exponents. Let's look at number 12. We have 1/3 is equal to 1/3 to the x power is equal to 27. Now 1/3 can be written as 3 to the -1 power. And 27, it would be nice if we could write that as 3 to a power. 3 to the 3rd power is equal to 27. You can confirm that on your calculator. 3 to the 3rd, 3 times 3 times 3 is 27. So what I did here was I rewrote 1/3 is 3 to the -1. 27 is 3 to the 3rd. The reason why I did that was so that we have this base is equal to this base. So we want the exponents to be equal. Using the rules of exponents, again, if you have a to the nth power, power to a power, you multiply those exponents together, m times n. So 3 to this power to this power, power to a power, you're going to multiply -1 times x to get -x equals 3 to the 3rd power. All right, look what we have here. We have an equation where this base is equal to this base. So this exponent has to equal this exponent. Like we're going to drop the bases and we get an equation that is -x equals 3. So x is equal to -3. X is equal to -3. We can check our answer. -3 is a solution. And you can also check on the calculator. Take this answer, x equals -3, and plug it into the original equation for x. 1/3 in parentheses raised to the -3 power. That equals 27. We know we've got the right answer because when you go back and check it, both sides of the equation are the same.